All right, so gases, they have different chemical properties from solids and liquids, but it's very similar physical properties. So let me go over a couple characteristics of gases. So you guys should be familiar with this from just everyday life, but I'm just gonna go over them just so that we have them kind of listed out. Okay, so number one, hey, shh. Nothing is more important than gases. And I know you're not talking about gases. Anyway, so mixtures of gases, when you mix gases together, they behave physically as one, basically one gaseous material, even though they're made out of different compounds. So for example, if you guys, you can't see it, but the air around us is made up of a lot of different kind of gases, right? But they all behave as if they're one substance. That's what mixtures of gases do. They act as if they're one kind of mixture. So that should be pretty self-explanatory. Again, you guys don't need to copy all this down word for word. This is already on Canvas, and yeah. All right, number two, gases expand to fill their container. So whatever container the gas is in, that is the volume of the gas. So very easy way to visualize this. If I fart right now, eventually it will spread and expand to all the corners of the room. And so the volume of the gas will be the volume of the room. However, before it comes out of my butthole, the volume, everyone has a butthole, it's anatomy. Okay, but before it comes out of my butthole, the volume of the gas is the volume of whatever sac holds it, right, inside my body. So the volume is small, but once I let it out, the volume expands to fill the container. I'm not taking questions on that. Okay. That leads to the next thing. Gases are highly compressible. For example, with the fart, it is compressed inside my body. But when I let it out, it expands. And so gases are very highly compressible. All right, and lastly, gases form homogeneous mixtures regardless of their identities and the proportions. So for example, your fart is made out of a lot of different types of gases. You got nitrogen, you got some sulfur, you got some methane, that's what makes it flammable. And there's all these different types of gases, but we recognize it as one kind of mixture, right? It's just fart. And so that's what gases do. They form homogeneous mixtures. Okay. All right, any questions on the properties of gases? It's crashed. Okay, mine did too. That was weird. Okay, so let's move on. So when we're talking about gases, we have to talk about a lot of different types of properties. So gases, when we study gases and do calculations with it, we're going to be working mostly with 4 different properties of gases. And that's pretty much what all our calculations will revolve around. So let's start with the first one. Okay, so the first one is pressure. Now, you guys all know what gas pressure feels like, right? When you eat Taco Bell and it's not digesting too good, you feel that pressure inside your stomach, right? Everyone can relate? Yes? Or it's just me? Okay, well, Taco Bell, beans, whatever, right? There's always some type of food that makes you feel that gas pressure. Now, the reason you feel that pressure is because the gas molecules, they're flying around, okay? And they hit the walls of whatever container they're in. So when it is inside your intestines or your rectum, it bounces on the walls and creates pressure. Okay, so think of pressure as how hard the gas molecules are hitting a surface. That's the first property of gases that you need to know. Okay, pressure is how hard the gas molecules hit the surface of the container they're in. Okay, so here we have low pressure because we got a lot of space and the gas molecules are not hitting it as much. But here, if the gas molecules are compressed like that, they hit the walls of the container more frequently or harder, and that creates more pressure. Yeah.
When you like feel like your ears are popping at an airplane, is that because of low pressure or high pressure?
It's because of the pressure change. It's adjusting to the pressure change.
All right.
Yeah.
Is it getting lower or higher?
Usually it's getting lower. Yeah. All right. Any questions? Hey, these fart examples are helping you understand though, right?
Absolutely, yes.
Yes. Okay. I'm definitely not doing this because I think it's funny. Okay. So pressure, and we symbolize pressure with P. Okay. All right. Second, what is it? Property of a gas you guys need to keep in mind. Oh, actually, before we do that, sorry. There's a lot of different ways to measure pressure. These are all different ways. Now I'm going to tell you guys the most important ones that you need to keep in mind. The most important one are the first three. Okay. One, ATM. So ATM stands for atmospheres. Okay. So we can measure pressure in units of measurement as atmospheres. And that's the air pressure at sea level. So Long Beach is pretty much sea level. So the gas molecules are flying around right now and they're hitting you, right? And the pressure they're hitting you, the force they're hitting you with is 1 atmosphere, 1 ATM. Another way we measure pressure is mmHg, that's millimeters of mercury, and that's equal to 1 ATM, 760. And then the third one that's really important is going to be 760 torr. Okay. I'd say as long as you're comfortable working with those three, you should be pretty good. On your homework questions, you might see things with pascals, PSI, but these are the most commonly used ways to measure pressure. Yeah.
Why mercury?
Because you know what a barometer is?
Yeah.
It's like a thing that measures air pressure, and they use mercury, and it's the millimeters it goes up in the barometer. Yeah. It's the old way of measuring it. All right, any questions on that? So again, ATM, mmHg, torr, that's just the units of measurement. It's how we measure pressure. All right, let's talk about the next characteristic of gases. The second that's important is volume, which we symbolize by V. And you guys know what volume is how much space something takes up. Okay, now gases are interesting because they expand to fill their container. Okay, so the key thing about gases is the volume of the gas is equal to the volume of the container that you put it in. And then we usually measure it in milliliters, liters, centimeters cubed. So let's say, for example, again, fart, right? Let's say I fart into a 1 liter bag. Okay? Somehow I get my fart in a 1 liter bag. And let's say my fart, I have a 0.1 grams of fart. Okay, that's the mass of my fart. When that 0.1 grams of fart is in the 1 liter bag, what is the volume of my fart? 1 liter. Okay, but however, let's say I pop the bag and then it comes out into the room that we're in. Let's say the room that we're in, for example, is 1,000 liters. Okay, it's still 1 gram of fart, but what's the volume of the fart? It's 1,000 liters. So you can have the same amount of a gas, but the volume will be whatever the container it's in. All right? Yes.
So is it kind of like molarity, but with gases?
Just the volume part of molarity. Yeah.
Okay.
We will be finding molarity of gases. All right, any questions on volume? That should be the easiest one, probably. All right, next is temperature, which we symbolize with T. Now, temperature, we have to be very scientific about the way we describe temperature. And the definition for temperature is not how hot or how cold something is. It's the kinetic energy of the molecule. So molecules are moving around, and temperature measures just the energy that they have as they move around. Yes.
What would you call how hot or how cold?
So we're going to talk about that in a second. So in a hot gas, right, when we call something hot, the molecules are moving faster than something that's cold. Okay. So for example, in ice is still water, right? So it's H2O. The H2O molecules are moving, but they're not moving very much compared to water, which is less cold than ice, and so the water molecules are moving more, so the temperature is higher. And then when you boil it and turn it into water vapor, those molecules are moving a lot more than the previous water molecules. Okay. So temperature is just talking about how much energy, the movement energy, kinetic energy, the gas molecules have. Right now, so for temperature, the way we measure it is, I know in the US we measure it in Fahrenheit, but in chemistry we're going to be measuring it in either Celsius or something called Kelvin. Okay. Okay, so the interesting about Kelvin is there is no negative Kelvin. Okay, we use Kelvin because it's really nice for chemistry, because 0 Kelvin is when the molecules are not moving at all. We call that absolute zero, which is physically impossible. But we use 0 Kelvin as when molecules are not moving, and as the number goes up, the molecules are moving more. That's what it's talking about. And this is a conversion from Kelvin to Celsius. Yeah.
Maybe we're gonna like really close to achieving absolute.
Yeah, we can get pretty close, but it's physically impossible, yeah, to get actual absolute zero. But I mean, they come extremely like percentages, like 0.0001.
How do we know that? How do we know that?
Because the universe is still connected. If you observe something, you have to use light. Light has energy. It's gonna heat up what, even if it's like infinitesimal, it's gonna heat it up. Yeah. All right. So let's use the Kelvin temperature or the Kelvin equation real quick. So I want you guys on your phones or Chromebooks to look up the weather today. And I want you to convert it into Kelvin. Okay. I want you to look up the weather for today. It might give it to you in Fahrenheit, but it should also give you Celsius. I want you to convert today's temperature into Kelvin. Okay, so I looked up weather in Long Beach and I got 81 right now. As long as you got something close to that, hopefully it's fine. So 81. You got 89?
Yeah.
So that's 81 degrees Fahrenheit, but we're looking for Celsius. Okay, so I didn't give you the thing for Celsius, but am I blind?
Yeah.
Ah, thank you guys. I'm such a boomer. 27. So 27 Celsius. Okay, as long as I have something similar. 27 Celsius.
Fahrenheit Celsius is -32 times 5
Okay, and then what you have to do is just very simply add 273.15, and that's gonna give you 315. Okay, that's it. So just keep in mind, as we do this unit, you have to turn all the Celsius into Kelvin, okay? You can never do calculations in Celsius because all the math is dependent on it being an absolute scale. Okay, so we use Kelvin because it's just easier to do the math. Right? All right, everybody good with temperature? All right, now before we move on, we have to talk about something very important in gases, and it's called STP, Standard Conditions for Temperature and Pressure. And basically STP, just putting it very simply, is if you change the pressure and the temperature, the gases will change quite significantly. And so in order to do experiments consistently, scientists, chemists like to work with gases at STP. Basically, STP, when you see it for your purposes, just know it means that the pressure is 1 atm, the temperature is 273.15 Kelvin. Okay. This is the most important part. STP just means the pressure of that gas is 1 atm, and the temperature is 273.15 Kelvin. Okay. But it's just a way to standardize our experiments. We aren't going to be doing, actually we do have a gas experiment, but we're not going to be really manipulating the gases. So just know that it's pressure and temperature. All right, so the fourth and final property of gases we'll be talking about are the moles of the gas. And this is just talking about the amount of the gas, okay? And so amount of gas, we measure it in moles, which symbolize with N, but we can also convert that into grams, right? So we also use grams to talk about the amount of gas, okay? And this is very simple. It's just how much of the gas there is, right? I have a little fart, small moles. If I have a big fart, a lot of moles. Okay. That's it. Those are the four properties of gases. Do you guys have any questions about them? We got pressure, volume, temperature, and moles.
For the pressure formula, F over A, what is F over A?
Force over area. So how much force is in an area? you don't really need to use that. Yeah,
So Kelvin equals 0 Celsius, 273.15 Kelvin.
That's correct.
0 Celsius,
Yeah.
right? So how could water be at STP?
so they wouldn't work with water.
Oh,
Yeah, it's typically not to work with water molecules.
okay.
Yeah, great question. Yeah, water freezes them. It's also nice because they can get rid of the water in the water vapor in whatever gas sample you're working
What
with.
is it 0? I thought water was like,
Water.
or sorry, what evaporates? Yeah.
Nothing. There's still gases. Oxygen is a gas at 0. Nitrogen is a gas at 0. Yeah. All right, everybody good with those 4? Sorry, is my handwriting dog? Which one? Which one is hard to read? Right here? N. The letter N, yeah. I apologize. And then we can convert to grams. Okay, so let's move on to the actual math part that we'll be doing. So in gases, we're gonna be using these things called gas laws. And these are some equations that a bunch of very smart nerds came up with to help us see if I change one of these properties of a gas, how do the other properties change? And some of these might be like common sense, but it's a way for us to calculate it, okay? So let's go into the gas laws. There's a couple that we'll need to know. We're going to start with the first one, okay? It's called Boyle's Law. Boyle's Law. Okay, and Boyle's Law tells you at constant temperature, when the pressure goes up, the volume goes down. All right, so that's Boyle's Law. P1 V1 equals P2 V2. So pressure and volume, the key thing is pressure and volume, they move in opposite directions, okay? All right, next one is Charles' Law. Charles's Law. Okay, now Charles' Law, I hate Charles too, okay, is at constant pressure. If you, basically easiest way to think about it is if you heat up a gas, the volume will increase. If you heat up a gas, the volume will increase, and if you cool down a gas, it will decrease. So, is there anybody who's put a balloon in a fridge before? Yeah? Okay. Thank you. I'm not the only weird one. So, when I was a kid, I thought my balloon would die if I just left it out. So, I put it in the freezer, and then I came back the next day as a kid, and it was like shriveled up. And I was very sad. But that is a perfect example of Charles' Law. If you decrease the temperature of a gas, the volume of a gas will decrease as well. What's up? Hold up. You're being recorded.
I guess you're big.
What? You're going to give me $1 million? Got that recorded. All right, so that's Charles' Law. Make sense, guys?
Hey.
Easy way to think about it.
So good to see you guys. Thank you for saying hello. Good to see you too. Thank you. Keep recording.
You're good. Easy way to think about it. When you guys exercise, what happens to your body temperature? It goes up. Okay, now, have you ever had to fart or poop while you're exercising? And the hotter it gets, what happens? The more pressure builds up, right? And I don't think that's the only reason, but I like to think of Charles' Law when I experience that. As my body temperature gets higher, the gas gets bigger. And as the gas gets bigger, right, there's more pressure inside. So that's Charles' Law, yeah.
Why does it gas?
Because so I'm going to talk about this later, but it increases the kinetic energy of the gases. More pressure, it spreads that, yeah. Exactly. Great question. All right, let's go to the third one. This is called Gay-Lussac's Law. Yeah, Gay-Lussac's Law. It's a French name. Grow up, guys. Okay? I think it's actually Gay-Lussac, but it looks like Gay-Lussac, so I say Gay-Lussac, but I'm not very sophisticated. All right, but anyway, very similar to Charles' Law, same formula. Oh, sorry, make sure you guys got the formula for Charles' Law. It's the same thing as this. We'll go over in a second. But in Gay-Lussac's Law, if you increase the temperature of something, the pressure will also go up. That's basically what Gay-Lussac's Law is. And if you cool down a gas, the pressure will go down. So same example as earlier. If you're working out or exercising and your body gets hotter and hotter, that fart inside, there's more and more pressure that builds up until you blow up. Yes.
So if you were to take more than this and heat it up enough, if it weren't to burn up, would it just go up?
Probably not. I mean, all the gases would dissolve, and then probably the liquids would dissolve before
Okay.
it just blows up. Yeah, it'll probably melt before it blows up. That's a question a serial killer would ask.
So I can't blow up a cheeseburger by heating it up.
No, the gases would evaporate. You just burn it. Yeah.
Oh.
All right, so that's Gay-Lussac's law. And then if you guys didn't get Charles' law, it's very similar. Charles' law was this right here. V1 over T1 equals V2 over T2. Okay. All right, and then we can combine all three gas laws together to form something called the combined gas law. And the combined gas law just allows us to see how all of the variables are connected and how they change one another. Okay, and those are 4 gas laws. We have a couple more, but we'll stop right there before we do some practice problem. But you got any questions? Ask him now, because Pepic's here and he's a better teacher than me. So I don't think they have any. Yes.
Wait, was that last part recorded?
Yeah.
Okay.
If the combined gas law is a completion problem, would it be constant at T?
Yes. All right. No questions for Pepic.
Alright, I'm good.
They're intimidated by you. Yeah.
Oh yeah,
That
just
happens. Hey, that worked a lot better.
No, I could do have a question. How do you feel that he's not using the bowl bath anymore?
What's
Hey.
that?
How do you feel that he's not using the
Hey, she has a real question. Hold up. Yeah.
Again, the combined gas law ratio, would that just be, how would you write it?
So I think it's easier if we do the problem together. So if you could hold on to that for a second, and if the questions don't answer your question, let me know. We'll talk about it, okay? All right, so let's do some problems before class ends. Okay, so I'm gonna do 5.2 with you guys, and then I'll have you guys do 3 on your own. But here it tells us we have a sample of gas, and the volume is 2.4 liters. So what I'm gonna do is I'm just gonna label all the numbers that we get. So obviously 2.4 liters is volume. So volume is 2.4 liters. And it says the pressure is 1 ATM, my favorite J. Cole song. It's a banger, dude. All right. And then it's asking what volume. So it's asking for V now. So we're looking for volume. And if would the gas be if the gas had a pressure of 4.9 ATM. Okay, so this would be P1 and V1 because this is where the gas started. Volume of 2.4 and pressure of 1.5. And if the gas changed to 4.9 ATM, what would be the volume? Okay. So I'll let you guys copy that bit down, but do you guys have any questions on why we labeled all the numbers the way we did? Or that makes sense? Okay, gas started at this volume, 2.4, and this pressure. And then it changed to 4.9, which is why that's P2. And then we're looking for V2. Yes.
Is the volume always just like
Huh?
Is the volume always this?
It could be a different unit of measurement, like milliliters, centimeters, cubed, as long as you keep them constant, the same one, consistent. Sorry, that's a better term. You're fine. All right, so if we take a look at these variables, which one of the gas laws do you think we should use? Yeah, Boyle's law, because you see P and V, right? So we got P1 V1 equals P2 V2. And so to solve this, all we do is plug and chug. We got 1.5 ATM, 2.4 liters equals 4.9 ATM times V2. Okay. So let me give you guys about a minute or so to write all that down. See if you could punch into your calculator and find the volume. All right, so we're gonna pull out our calculator. Okay, and then on the left side we have 1.5 times 2.4. And then to isolate V2, we're going to divide both sides by 4.9, and we should get a volume of 0. And I'm going to keep it at 7.3, and the unit of measurement will be liters. Okay? Everybody okay with that? All right. So let me give you guys about 2 minutes. See if you guys can do 5.3 on your own. You got to figure out what variables you have and what gas law you need to use. Okay, so I'll give you a second to work on. Okay, so here we start off with volume, so 12 liters. So we have a gas that has a volume of 12 liters, and it's collected at 38.8 degrees Celsius. So the temperature is 38.8 degrees Celsius. And then it's asking us to find the volume. So we're looking for V when the temperature is at negative 39.9 degrees Celsius. Okay, so if we take a look at these variables, which gas law should we use? Yeah, Charles' law, V1 over T1 equals V2 over T2. Okay, unfortunately, we cannot plug it in exactly the way we have it. Does anyone want to guess why? Yeah. Yeah, if you guys notice, all the temperatures are in Celsius, right? And I mentioned earlier, you have to have the temperatures in Kelvin. Okay, so if you didn't do that, it's all good. Now you know. So we have to turn the 38.8 into Kelvin. So we're gonna change that to 311.95. So 311.95 Kelvin. And then here we have 273.15 minus 39.9, and we get 233.25 Kelvin. Okay. Okay, and hopefully if you just put in the Celsius, you notice you get a negative number. And it's impossible to have a negative volume. And so, yeah. All right, let's plug it in. So we got 12 liters on top. We got 311.95 Kelvin on the bottom equals V2 over 233.25 Kelvin. Okay, and then for the math, we're going to do 12 divided by 311.95. And then we're going to multiply that by 233.25. And that will give us a value of 8.97, something around there. Okay, so the volume will be 8.97 liters. What's up?
I'm not gonna leave early so I can work.
You have an early out?